Yes, thank you, Aaron, for this kind introduction. Yeah, I'm going to talk about some work I did with my collaborators Alessio, Kevin, and Benjamin. And currently it's available as a preprint on arXiv, as you see here. So the outline of my talk is roughly organized in 3 parts. So I will start with a general introduction to give a setting for what I want to talk about. Then this talk will be in what we've heard already a few times in this seminar series, and most recently by Benjamin 2 weeks ago. I will use the essential or ideas of the essential renormalization group in quantum gravity. So I will introduce this concept and apply it here to the derivative expansion. So this is what I will talk about in the second part of my talk. And then in the end, I will show you some results that we get from this approach and discuss them in the context of quantum gravity. So let me start, and I want to start just by discussing a bit of gravity itself. So gravity is, of course, maybe the oldest known force of nature that we are aware of, and we have classically a very well description of it in terms of general relativity, which has been verified in numerous experiments from early days, such as the perihelion precession of Mercury, more recently also including gravitational waves and black holes. And we have even had the opportunity to see pictures of the black hole by the Event Horizon telescope now. But even though classically we have a good understanding of gravity, we know that there are some challenges that we have to face. And this is because we know that there must be something beyond the classical regime of gravity, and that's what we refer to as quantum gravity. And this is because all of the fundamental forces that we know of, except gravity, are formulated as a quantum theory, or more specifically as a quantum field theory. But gravity has some challenges that we face when we try to incorporate it into this concept. And if we don't do that, then we also know that we get problems, for example, the black hole information paradox, and similar issues if we try to treat gravity as a classical theory and the other forces as a quantum theory. So we know that there must be something beyond the classical regime of gravity. And we have to figure out what it is, or how we can formulate gravity as a quantum theory. And the problem that we face here, of course, most of you will know this, is the non-renormalizability of quantum gravity, or perturbative non-renormalizability. And this means if I start with the Einstein-Hilbert action of gravity, which is just here given in terms of Newton's coupling and the cosmological constant, then a perturbative analysis shows very quickly that, mostly coming from the fact that Newton's coupling has a negative mass dimension, that divergences show up in perturbative computations, which can only be renormalized by including higher order operators into the action. So at tree level, we might start with the Einstein-Hilbert action. At one loop, we have to include quadratic curvature invariants, so fourth powers of derivatives. And then at each higher loop order, for example, as 2 loop, we get higher derivatives. And at 2 loop, we end up with the cubic curvature invariants, which contain 6 powers of derivatives. A full list of these curvature invariants that shows up is given here in this table. And you see, so the point of this table is just to show that the number of terms that you have to include in this action quickly rises to large numbers already at the dimension 6 curvature invariants. If you restrict yourself to 4-dimensional space-time, you, I think, have 10 independent curvature invariants that you have to include here. So this action quickly becomes very involved and complicated. And of course, what this means is that if you don't have, because each of these curvature invariants also come in with different couplings, if you don't have any mechanism to set or give these couplings some values, then you get this naive breakdown of predictivity, because if you have an infinite number of couplings in the action, you require an infinite number of measurements to give values to these couplings, then your theory doesn't have any predictivity. Of course, you can still formulate it as an effective field theory without any such mechanism, because at low energies, all these higher order operators are suppressed. But if you want to go beyond the Planck energy or the Planck mass, then you will quickly run into this problem, and then you need some mechanism to predict these values of these couplings. Of course, this explanation so far is a bit simplified, simply for the reason that not all of these operators that I've shown you so far contribute to physical observables, such as scattering amplitudes or S matrix elements. And basically, we can classify couplings into two categories. One of them are inessential couplings, such as the wave function renormalisation, that do not affect observables. And also, we can change them if we redefine the quantum fields that we have in our action. Contrary to that, we have essential couplings. These are, for example, gauge couplings, and they do not change under field redefinition, so they do affect the physical quantities. And with these two categories, of course, we are mostly interested in the essential couplings because they actually affect physical predictions that we can compute from the theory. So we would like to figure out what these essential couplings are. And if we restrict ourselves to the universality class of GR, that means basically that we just want to have the degrees of freedoms that are present in general relativity, so massless spin 2 degree of freedom, and not ghosts such as they would show up in stellar gravity. Then we can figure out what the inessential couplings are, and also then what the essential couplings are, just by seeing what terms vanish when we impose the classical equations of motion, so the Ricci tensor being 0. And if we do this to gravity, then this table that I was showing you before reduces to just 3 different essential operators that we have to take into account. So this is the Newton coupling that corresponds to the Ricci scalar here. Then at the quadratic curvature invariance, we only have one term that becomes essential. The other term, so this the box of acting on the Ricci scale is of course a surface term, and then the other two curvature invariants here are inessential. And the remaining term here, which in the curvature basis I'm using here on the table, is the Riemann tensor squared. I can just absorb in the Gauss-Bonnet term, so a topologically invariant of gravity. And for this reason, at one loop, so if the one loop, because you only have to include the quadratic curvature invariance, the theory is actually renormalizable, at least in pure gravity, just because of the fact that these two terms are inessential and the other remaining term can be incorporated into the Gauss-Bonnet term. Now, if you go one order further, so at a 6th order in derivatives, then you again have that one term is essential, while the other terms are inessential. But at this order, I can't do anything like the Gauss-Bonnet term. I cannot absorb it into a topological term that does not contribute. And I really end up with a dynamical essential coupling here, which is the first one after the Newton coupling. And in the perturbative treatment, of course, we know that Goroff and Sagnotti and then later Van der Ven verified that this essential coupling indeed obtains a divergence in perturbation theory, and this is seen as a confirmation that perturbative quantum gravity really has this problem of non-predictivity at high energies. And of course, there might be a way out of it, and this is non-perturbative renormalizability in the sense of asymptotic safety. And this is, of course, why we are all here in this asymptotic safety seminar. And the idea first proposed by Weinberg, and then, of course, Martin had some very influential work trying to set it up in a non-perturbative way. So the idea is that, of course, we have some fixed points and that we flow into in the UV. This first of course avoids possible Landau poles that show up or might show up in the RG space. And also because we have to stay on this in this UV critical surface, which is spanned by the relevant direction of the fixed points. This can lead to a finite number of parameters that we have to take into account because if the UV critical surface is finite dimensional, then we still have a predictive theory, even though the coupling space is infinite dimensional. And this mechanism might be allow us to formulate quantum gravity in the sense of asymptotic safety as a predictive theory up to arbitrary high energies. So now I would like to assess this idea in a bit more detail, and I will do this in this, as I mentioned before, in the setting of essential quantum gravity. So first of all, we need some tool to find fixed points or possible fixed points of the theory and determine the relevant directions to see what the dimensionality of the UV critical surface is. And the most commonly used tool, of course, is the function renormalization group, as I'm sure you're all aware of, which was found by Wetterich first in 1993. And the idea, of course, is that we introduce some IR regulator into the path integral, which allows us to integrate out UV degrees of freedom mode by mode from the UV to the IR. And this then is a very common tool to apply to quantum gravity because it's non-perturbative, and we can even try to test it at non-perturbative fixed points and see whether such a fixed points exist in gravity. And of course, there's a long list of literature which has tried to apply this, and there's also a long list of evidence coming out of this that there is indeed a fixed point for quantum gravity. But in this talk, I would like to include the possibility of doing field redefinitions in this functional normalization group. So if you look into the path integral, the idea then is that usually we would couple the source to the quantum fields. So in the case of the graviton, we would have h mu, and we would couple the source to this h mu and the regulator as well. But here instead, I couple it to a composite operator, which I call chi. And this composite operator is a function of so the background field and the fluctuation of the graviton. And doing this, I can set up this functional normalization group, which then includes additional terms marked as red here. And these additional terms depend on this RG kernel psi, which just parameterizes the field redefinitions that I can do by using this composite operator chi in my path integral. And using this, I can explicitly see then what the effect of field redefinitions are on this functional normalization group and on the effective action that I can compute. So why do I want to do this? Well, the reason that field redefinitions can be relevant is that first of all, inessential couplings should not really be counted as parameters of the theory because they do not contribute to physical observables, as I mentioned before already. So if we count the dimensionality of the UV critical surface, then we should really focus on the essential couplings because these are the couplings that do matter if you want to make physical predictions of your theory. And then we can use the fact that inessential couplings change by field redefinitions in contrast to essential couplings, which do not so. And therefore, using these field redefinitions, if we include this in the functional normalization group, we can use it to change inessential couplings and impose different RG schemes that fix them to some values. Of course, there are some remarks that should be made here if we use the field redefinitions, as Benjamin mentioned 2 weeks ago in his talk, which was also in the essential normalization group of quantum gravity. And one of these remarks is that these field redefinitions should not change the degrees of freedom that we have in gravity. So we should not remove or introduce a new degree of freedom by these field redefinitions, because then, of course, we do not have this invariance anymore. Of course, in this talk, I will talk about the derivative expansion. So I will restrict my field redefinitions to be local and have a finite number of derivatives. So I don't have to be that careful in with this remark and changing the field redefinition, changing the degrees of freedom, because I only have local field redefinitions that I worry about here. And then, of course, I will use what's known as the minimal essential scheme, and this was first introduced by Alessio, Kevin, and Ricardo 3 years ago now. So the idea of this scheme is that we can take the inessential couplings of the theory that are usually present, and using these field redefinitions, we can just set them to 0, or all the couplings that we can set to 0, we'll set to 0. And the reason for this, I mean, there are basically 3 reasons why we do this. First of all, this leads to technical simplifications, as we will see a bit later in this talk as well. And also, using this, we specifically set inessential couplings to a finite value, in this case 0, so they're not running anymore. And in this sense, I don't have to worry about misinterpreting them as free parameters of the theory that would have to be fixed by a parameter on the UV critical surface. Also, I already mentioned that the quadratic curvature invariants are all inessential except for a topological term. And this means if we set the inessential terms to 0, then we do not get any ghosts from the quadratic curvature invariants, such as would be present in stellar gravity. And this is, of course, a very useful property if you think about this in terms of unitarity, because we don't get these ghosts anymore. Now, of course, a very important question is which operators are essential and which operators are inessential. I already mentioned that you can see this by implying the classical field equations. And here I also want to show this from a different point of view, maybe by, namely by showing you how this RG kernel or the field transformations explicitly tell you what terms are essential and what are not. And to do this in this functional normalization group, we just start with the general parameterization of the RG kernel that contains all the terms that we want to consider up to a given order in the derivative expansion. So here in this talk, I will go to sixth order in derivatives, or cubic order in curvature. And this means that in this RG kernel, I have to take into account all terms that have up to 4 derivatives. And this starts with the simply with the metric. And then I have 2 terms that are second order in curvature. And then I think there are 10 more terms that are quadratic in curvature or fourth order in derivatives as seen here. So this is just a general parameterization that I can write down. You see that there's for some technical choices, or for simplicity, we have shifted some of these contributions here, but this is just by our choice. In principle, you can just write down any basis that parameterizes these symmetric tensors up to fourth order derivatives, and this parameterizes the field redefinitions. And with this parameterization of the field redefinitions, we can now see what terms are essential and what are inessential in the effective action in the action. And to do this, we just look into this term, which is the effect of the field redefinitions that we see on the left-hand side of the flow equation. So this is basically the classical part that we see. And putting in these field redefinitions, we then get an expression for terms that are generated doing these field redefinitions. And we see that there's a lot of terms generated, and all of these terms that are generated are inessential operators, simply because these gamma functions, which are just the parameters here in this RG kernel or in this ansatz, I can just choose values for these gamma functions so that the value of this operator, for example, gets changed to whatever value I want in the action. And this is just following from these field redefinitions. And then, since all of these terms that show up here must be or should be inessential couplings, the terms that do not show up here are the essential couplings. And these are Newton coupling. So you see here that the Newton coupling or the Ricci scalar shows up here with the gamma G, but the gamma G also shows up for the cosmological constant or the vacuum energy. So actually you have to like look a bit deeper into the equations and see whether the Ricci scalar or the vacuum energy is inessential. But you can then see by studying the dependence of critical exponents that it's actually the vacuum energy that should be inessential, while the Newton coupling is essential. And then you see just that, as I mentioned before, the quadratic curvature invariants, so Ricci scalar squared and the trace as Ricci tensor squared, which is this S mu, they show up as inessential couplings. And you see, importantly, that you do not get a Goroff-Sagnotti term here. So this is this Weil tensor cubed. And this means that the Goroff-Sagnotti term is an essential coupling because it does not get produced here by using these field redefinitions. Alternatively, we have already seen before that the Goroff-Sagnotti term is also not set to 0 by imposing the classical field equations of GR. And therefore, it is an essential term. Also, the Gauss-Bonnet term, as I mentioned before, is an essential coupling, but of course, this is a topological term. So it does not really affect the beta functions of other couplings. So now we have figured out what terms are essential in our action. And I've marked them here as, so the most important terms I've marked here as red. These are the Newton coupling and the Gaussian coupling. And these are the 2 dynamical essential couplings that we have in quantum gravity at 6th order in the derivative expansion, at least in the universality class of GR. We also have the vacuum energy. We cannot set the vacuum energy to 0 because we want to be able to flow to the Gaussian fixed point, and this imposes a restriction on the value that the vacuum energy can take. And this regulator dependent value is then seen to be 1/8 pi. which we just write into the action. But importantly, again, the value of this vacuum energy does not change as we change the RG scale. So it does not run. It's just fixed to some value using this field redefinition. Of course, we also have the Gauss-Bonnet term or the topological term as a coupling here, as an essential coupling, which does show up, but since it's topological, it's not a dynamical coupling in our theory. So really the two important dynamical couplings that we have are the Newton coupling and the Goroff-Sagnotti coupling. Okay, so this sets now the minimal essential scheme that I will use as sixth order and the derivative expansion. And I want to briefly mention some of the technical choices that we choose to study now, because of course we have to put in the functional minimization loop some sort of gauge fixing, and we have to choose a regulator. And for the gauge fixing, we just choose a standard harmonic gauge, which is given here. And this will, as I show you on in 2 slides, I think, lead to a very simple form for the propagator, which is the reason why we choose this harmonic gauge. For the cutoff, we will use a lithium regulator, so that is given by this form. And to have some parameterization dependence, which we can use to study the parametric dependence of the fixed point on some unphysical parameters, we write this parameter alpha into this RG kernel. And so this basically allows us to study the stability of the fixed point in terms of some unphysical parts that you can write into the regulator. We also include non-trivial endomorphism into the traceless part of the graviton. So if you look into the traceless part, then we write this parameter beta into the Laplacian that we have in the regulator. And this again is another parameter that we can use to study the dependence of these unphysical parameters of the fixed point. Particularly for beta equals 0, we have also what's known as the type 1 cutoff in the literature. And for beta equals 1, we have the type 2 cutoff. So in this case, for type 2, this endomorphism is really chosen to be just the curvature bit that you get from the variation of the Einstein-Hilbert action. And so absorbing this into the Laplacian of the regulator really corresponds to the type 2 cutoff. And yeah, below I will study, I will first show you the results for alpha and beta equals to 1, but later on I will also show you what happens if we change them and have non-trivial values for them. So I want to give some brief remarks about, so once we have now fixed this minimal essential scheme and the gauge fixing and the regulator, how we can actually compute everything using the functional normalization group. And so this basically corresponds to solving this the functional normalization group equation here, and using one of the nice parts, and which is what I mean mostly when I say that the minimal essential scheme leads to some technical simplifications, can be seen in the propagator on the Hessian of the effective action. And this is because if you use the minimal essential scheme, and the important point is here that the quadratic curvature invariants have been set to 0 apart from the topological term, then this Hessian just includes from the Hessian of the Einstein-Hilbert term, and using the gauge fixing that I've chosen, it's just the Laplacian of our theory. So there are no other terms that contribute here. Now, if I include the Goroff-Sagnotti term and potentially other essential couplings that come after the Gaussian term, I will also get contributions as curvature bits. But I can take care of them just by expanding everything on the right-hand side in this functional trace by expanding it in curvatures. And then I have to take care of some commutators using the Baker-Kemper-Hausdorff theorem. But the fact that the Hessian here only includes the Einstein-Hilbert part and does not include higher powers of derivatives without the curvature really simplifies taking the inverse of the propagator here and makes the computations much more usable or user-friendly. Of course, I say that it's using the minimal essential scheme, it's much easier to do those computations. The computations are still really involved. And to show you this, I just show you a heat kernel here. Of course, after expanding the functional normalization group to some order on curvature, which is in our case the cubic order on curvature, we have to trace the functional trace, and for this we use off-diagonal heat kernels. And the heat kernels that you have to use are really long. And I've just taken this from a paper from Goroff et al. From 2011. And this just shows you the cubic heat kernel that enters into these equations. So basically what you have to do is you do this curvature expansion of the right-hand side of the functional normalization group, which already is a very long expression. And then you have to introduce the heat kernels as well. So this is really quite a messy situation. And it means that calculations by hand are not really doable. And instead, we have to use a computational setup and using computer algebra to solve the flow equation. And an important point that I want to mention here that we did is we used two completely independent computational setups to compute this flow equation. So one of these setups is based on the exact package for Mathematica, which was written by these gentlemen here. And it has previously also been used by Benjamin and similar computations in terms of asymptotic safety. And so, yeah, this is one computational setup that we use to derive the flow equation. Then completely independently of this, we also have some completely self-written Mathematica code together with form, and used the second setup to also compute the flow equation. And of course, both of these setups that we use give us the same results. And this is, of course, a very important cross-check that we kind of have to do, because otherwise doing these really long algebraic equations, it's very easy to have an error somewhere or implement a bug somewhere. But the fact that we have these really two different setups giving us the same results makes us quite confident that we actually have computed the correct flow equation. So with this, I actually want to talk about the results that we find. So applying this minimal essential scheme where we use field redefinitions to set inessential couplings to 0, and applying this to sixth order on the derivative expansion. And as I said, in this case, we have two dynamical essential couplings. These are the Newton coupling and the Goroff-Sagnotti coupling. And I'm showing you here just the phase diagram of theory that we get. And here at vanishing couplings, we have, of course, the Gaussian fixed point, which we know corresponds to the IR behavior of gravity that we know of. And importantly, we also have a non-trivial fixed point as is required for this for the asymptotic safety scenario. And this is located in this phase diagram over here. So this color spectrum that I'm showing in the background just corresponds to the strength or the magnitude of the RG flow, and the arrows correspond to trajectories that we have in this diagram. Most importantly, there's exactly one trajectory that connects the non-trivial fixed point to the Gaussian fixed point. So there's this trajectory which flows from this UV fixed point in this case to the Gaussian fixed point, and the fact that there's just one trajectory means that we just have one parameter or one relevant direction of the fixed point. So there's no other parameters that we have to fix. There's just this one parameter which is set by the scale setting of the theory, and no other free parameters in this pure gravity example. So in this sense, gravity is as predictive as it can be. What's also worth noticing is that while Newton's coupling has a value of 0.3 or 0.4 roughly, the Goroff-Sagnotti coupling at the fixed point is really, really small. So it's actually some number of times 10 to the minus 7. And this is the value that it takes at the non-trivial fixed point. And then, of course, at the Gaussian fixed point, it just goes to 0. So the Goroff-Sagnotti coupling is throughout the whole RG trajectory very, very small. Of course, I forgot to mention that the fact that the Gaussian coupling is irrelevant, of course, is a verification of a previous study from 8 years ago now, where this was studied also in the standard scheme. Of course, this was not a complete derivative expansion as we are doing here, but instead they were just taking into account the Einstein-Hilbert term and the Goroff-Sagnotti term, while all quadratic order curvature invariants and other cubic curvature invariants were neglected. Here we, in this minimal essential scheme, we do not have these curvature invariants in the action, but we still take their effects into account using the field redefinitions. So in this sense, this is really the first complete derivative expansion to sixth order with an asymptotic safety. So I want to show you some more details about this UV fixed point. I already mentioned that it has one relevant direction. So this is seen here in the last line where I show you the critical exponents of the fixed points at the sixth order and derivatives. This is the relevant critical exponent, which is roughly of the order of 2, which is also the classical, or roughly the classical value for the critical exponent. And then the Goroff-Sagnotti term has a relevant critical exponent. But of course, but as we see here, this is not very large. It's roughly of the order of -4, which shows you that the critical exponent for the Gaussian term is really not that far off from its canonical value. I'm also showing you the values for the Goroff-Sagnotti coupling and these gamma functions again. So these gamma functions here are the parameters that enter in the field transformations that I was showing you before. And I already mentioned that the Goroff-Sagnotti coupling at the fixed point is really, really small. And similarly, you see that this also holds for these gamma functions of the field redefinitions. So except for gamma g, which is roughly the value of -1, all of these gamma functions, which corresponds then to the quadratic and the cubic inessential curvature invariants, have really, really small values. And together with the fact that the relevant critical exponent does not really change, and it's very close to its canonical value, this kind of tells us that this fixed point here is really, really close to perturbativity. So even though it is non-perturbative in the sense that it's not perturbatively, the theory is not perturbatively renormalizable, we have a fixed point that has very near perturbative features, such as a small value for the Gaussian coupling and small values for the gamma functions that we see that enter the field transformations. And this allows us even to do some kind of crude approximations. We kind of, for example, just throw out all of the gamma functions except for gamma g, because gamma g is the only one that's not really very perturbative because it's -1. And then try to see whether we still find the same fixed point. So doing this, we actually see that we do. So at doing this cubic order, or this expansional cubic order and curvature, and neglecting all of these gamma functions except for gamma g, we see that the fixed point is really stable. So the relevant critical exponent is just fixed to its value in the Einstein-Hilbert truncation, while the irrelevant critical exponent is just very small amount away from the full value at the 6th order and the derivatives, which we have here. Of course, this is really interesting because it should be contrasted to what we have in the standard scheme, which only differs from this approximation here by also setting gamma g to 0. And if you do this, this is what has been done originally 8 years ago in the first study of the Goroff-Sagnotti coupling and with an asymptotic safety. Then you see that the critical exponent for the Goroff-Sagnotti coupling is still irrelevant, but it's much larger. It's about of the value of, I think in the paper they report 80. Of course, I think there was an error, so I think the actual value was 20 for this critical exponent, which is irrelevant, but still large. And just the fact that we have this gamma g here changes the critical exponent for the Goroff-Sagnotti coupling quite dramatically to a value of -3.8. So even though these other gamma functions are not important at all to get this value for the Gaussian coupling of roughly -3.8, the value for for gamma g is actually really important, because otherwise you get a value for the critical exponent which is wrong by an order of magnitude. So far the results that I presented you here was for the parameters that I introduced earlier in the regulator alpha and beta equals to 1. And here I want to show you a bit what happens if we change them and don't set them to their trivial values. And in this slide here, I keep still the anamorphism parameter beta equals to 1. So I'm still having a type 2 cutoff here, but I vary alpha. So this is the parameter that we wrote in front of the regulator to see how the fixed point behaves under changes of alpha. And as you see in these plots here, if you go to either very small or very large values of alpha, the fixed point loses some stability, and this you can see as the Newton's coupling and the Gaussian coupling blowing up in these regimes, as well as the critical exponents. But most importantly, in between these regimes where we can't really trust the fixed point anymore, we find a large area where the critical exponents and the fixed point in general is remarkably stable. So this is seen here where the red line is the relevant critical exponent, and it's really close, always close to the value of 2 within this area we have a stability for the fixed point. I should mention that this gray band that we see here on the right-hand side is indicating at a point where the Newton coupling of the fixed point has a sign change. So while it is positive left of this gray band, to the right of it, it's negative. So this means this is an unphysical regime because we know that Newton's coupling should be positive. So the area in which we can really trust the fixed point should be cut off at this line, where also the Gaussian coupling, of course, has a divergence. And what's also an important fact here is that throughout this area from where the fixed point is stable, we have the relevant critical exponent to be, as I mentioned already, very or quite insensitive of alpha. And also the other critical exponent is always irrelevant in this regime. So throughout this whole regime where we have some sort of stability for the fixed point, we see that there's always one relevant critical exponent and the other one is irrelevant. Another important fact that we see here on this right side is the behavior of the derivative expansion between different orders. So we've already seen before that the critical exponents converge very well to cubic order in this table that I was showing you. And here I'm showing you basically the same in the whole alpha regime. So studying the dependence of the different orders for the relevant critical exponent independence of alpha. And while between the leading orders, so second order derivatives and fourth order derivatives, we do see that there is some change. This change becomes really small if we compare the effects that the cubic order curvature invariants have on top of the quadratic orders. And this is seen here by the fact that the red line, which is the cubic order curve or the expansion at sixth order derivatives, and the expansion at fourth order derivatives, which is the green dashed line, you can't really distinguish them anymore in the regime where the fixed point is stable. So this means that that this derivative expansion converges really well in this regime. And for this reason, we kind of can expect that higher order derivatives in the derivative expansion will not really change anymore the behavior of the critical exponents here, if this apparent convergence that we see here continues to be like this to higher order in derivatives. Here also show you again the regulator dependence or this alpha dependence for the gamma functions. So this these functions that parameterize the field redefinitions that enter the function normalization group. And we already saw at alpha equals 1, which is what we studied before in the previous part of the results, that this gamma g, so the gamma g parameter of the field transformations is of order of -1, while all the other parameters of the RG kernel are very small and perturbatively small, close to 0, except for, of course, the regimes where the fixed point loses some of its stability properties, which happens here for small alpha and here for large alpha. But throughout the region where we have a stable fixed point that we can trust, we see that the gamma functions are always really small, which is another sign of this near-perturbativity that I already mentioned before. So this is the alpha dependence of the fixed point. And I already mentioned before that I introduced this parameter beta before, which corresponds to the endomorphism dependence of the fixed point. And this is what I'm showing you here. So these are two plots where I show you the relevant critical exponent on the left-hand side here and the irrelevant critical exponent on the right-hand side. And we see the value of these of both of these exponents as a contour plot in terms of alpha. So this is this parameter in front of the regulator, and beta, which is the parameter of the endomorphism. And using these plots, we see how the critical exponents change as we change these parameters of the regulator. So the results I was discussing in the beginning corresponds to alpha and beta equals to 1, which is the point here and here for the irrelevant critical exponents. And here we see now how they all change throughout this 2D plane. In the top left, you see that there's some white area on both of these plots, and this is because in this area, the fixed point becomes a bit unstable, and there's just some very large fluctuations of the critical exponents. And so for this reason, I have excluded this area from this plot. But apart from this, you see that, again, the fixed point is really stable throughout the whole region. And in particular, relevant critical exponents, we see that its values just change between roughly 2.4 and 2. So it's always, again, relevant. And its value is really close to 2. And similarly, for the relevant critical exponent, you also see that it's always irrelevant, and with values reaching from, in this plot, from minus 1.5 to roughly minus 4 or 5. I'm also showing you these lines here on this plot, which correspond to some sort of PMS study that we performed here. So the idea of this is that we want to find within this 2D parameter range of the parameters alpha and beta a point which is special in the sense that the variation of alpha and beta of the critical exponents vanish. And this is shown by these two lines here. So the black solid line is a line where the dependence of the relevant critical exponent on alpha vanishes. And the black dashed line is the line where the dependence on beta vanishes. And you see that there's, interestingly, one point, which is, we call the PMS point, where both of these dependencies vanish. And there we see that the critical exponent has, according to this PMS principle, some sort of stability. And here I'll show you the same point at for the irrelevant critical exponent as well. Yeah, so I already mentioned that there's this large area of stability, and the relevant critical exponent takes values from 1.9 to 2.4. What's also interesting, and this is mostly shown here in this plot, where I plot you the value of the Goroff-Sagnotti coupling, now with the same dependence on alpha and beta, is that you have this very pronounced line at beta equals 1, which corresponds to the type 2 cutoff. And this line here is the point where the Goroff-Sagnotti coupling has a 0. And we have already seen before that the Goroff-Sagnotti coupling at the fixed point for alpha and beta equals 1 had the value of 10 to the minus 7. And the smallness of this Gaussian coupling can be seen here, but just by the fact that there's just a line in this plot where we have the regulator dependence, where the Gaussian coupling has a sign change and vanishes identically. And this is really interesting because it shows that the features of near-perturbativity of the fixed points, namely that the Gaussian coupling is small and that the gamma functions of the field transformations are small, is most prominent for this choice of the type 2 cutoff. Of course, we've seen in the slide before that even away from the type 2 cutoff, we have stable values for the critical exponents. But going close to the type 2 cutoff, or beta equals 1, makes this near-perturbativity and the stability of the fixed point most manifest. And I'm showing you here as well for the gamma functions of the field transformations again. So very similar to this point here, where we have 0 or a sign change at beta equals 1. We see that all of these gamma functions that enter this RG kernel have sign changes close to beta equals 1. So again, this kind of singles out the type 1 cutoff as maybe a preferred scheme to choose for the regulator, because we see that it makes the near-perturbativity of the fixed point most manifest. Of course, gamma G, as I mentioned before, is not having this property that it goes close to 0, but instead it takes values of the order of -1 throughout the region here. So throughout the whole alpha and beta region. And yeah, I think this brings me to my conclusion slide. So we have, I tried to show you that we find, using these ideas of the essential renormalisation group, a unique fixed point in the universality class of Einstein gravity, and it has just one relevant direction. So we just have one parameter that is fixed by the RG scale on the UV critical surface in pure gravity, and all the other couplings of pure gravity are just predicted by asymptotic safety. We've also seen that higher order operators, such as the cubic order or cubic curvature invariants, only induce very mild modifications of the results that we see at lower orders. And this can be explained by these signs of near-perturbative behavior, so that the Goroff-Sagnotti coupling is really small and that the field parameter or field parameterization or the RG kernel is very small at the fixed point. And this leads to the fact that we have a very stable result if we go to higher orders in the derivative expansion. Of course, there's several directions here for future work. One, or the first point, is to the inclusion of matter, because here I've only been talking about pure gravity systems. But of course, we know that there's matter out in the universe, so we have to see what happens to this fixed point, and it will be really interesting, I think, to happens to the stability of this fixed point and its properties when we include gravity matter systems. Benjamin has already done some first steps in this direction, but of course there's much more room to be explored. And also we might want to see what happens if we include even higher order operators, and using the minimal essential scheme, it might even be feasible to do this, so that we not go just to cubic order and curvature, but maybe even to quartic order and curvature, so 8th order and the derivative expansion. And finally, this is also, I think, one of the most important points that already came up, I think, 2 weeks ago in Benjamin's talk, is the behavior of the essential scheme beyond the background field approximation, because all of this talk that I was telling you here so far has been within the background field approximation, and it's, I think, really important to see what happens if we leave the realm of the background field approximation and include or go to some sort of vertex expansion and see whether the essential scheme that we have studied here in the background field approximation has the same properties if we leave the background field approximation, or maybe they're just artifacts of that. So I think that will be a really important question to settle in the future. And yeah, with this, I want to thank you for your attention.
Yeah, thank you, Yannick. Let's all give Yannick a hand before we open the floor for questions.